with integer linear programming and dynamic programming. That's actually we're just going to consider only these two topics today. So hopefully we'll go through that in some amount of detail. Dynamic programming actually is something that many people learn and then forget, and same thing happened to me. So I thought I'd go over it quite carefully and slowly because it's a very useful technique, and once you understand the heart of it, it can really be useful in many, many different places. All right. So I'll start with integer linear programming, and I kind of gave just a overview of it last time, saying that what's going on here is that we don't have we have a linear system which is nice, but it is not nice because the control variables, the xi's, are either 0 or 1, and so this kind of constraint on the control variables, it is either in this position or, I'm sorry, not 0. I'm confused. Okay, sorry. I'm confusing myself with something else. Okay. So imagine you have a control knob on your radio dial, right? So in a cheap radio dial, you have a knob and you can turn it like this, and you can have essentially real increments, okay, any real increment that you want. So if you have a station that's not coming in nicely, you can kind of tune it just so as you get a really good signal. With the integer constraint, what happens is you have, like, let's say the quantum is 0.1, you have 89.1, 0.2, 0.3, and it can be quite annoying because the radio station is between 0.1 and 0.2, so both settings are bad, and in fact it should be like something real. So in this case, a bad radio works better than a good radio, because a bad radio allows you to have complete precise control of intermediate points. So things are sort of easier when you have ability to have any intermediate position that you want. When you have integers, then things get kind of messy. And perhaps the easiest way to explain why things get messy is to consider sort of the canonical problem, and I'm going to consider the problem of scheduling. So I'm going to show you how to represent scheduling using a linear system, and we'll see what happens. So here we consider the following thing. We have two people, let's say A and B, and A and B have these jobs. Now, a job is something that you can, something that can get done, and you have some machine. So you have some machine, maybe it's a computer, maybe it's not, it's just a machine. And the machine has the constraint that it can only do one job per time period. Okay? So it can only do one job per time period, so it can be either A's job or B's job. So of course we need to know which ones, who should get the job. So we define the following things. So let's say we have the following table, and in this table we're going to do this. We're going to sort of draw these diagonal things, and the upper quadrant is the cost and the lower quadrant is the benefit. So this is for A, this is for B, this is for time period 1, this is for time period 2, and we'll just put some numbers in, let's say 10. So this is the cost. The benefit should be greater, hopefully. So 15, 1, 6, 20, 200. So I just picked up some random numbers. In fact, they don't even have to be integers. They can be real numbers. It doesn't really matter. What we're saying is this. If A's job gets scheduled in time slot 1, A gets, it costs A so many dollars and gets a benefit of so many dollars, or, or units. You can just ignore what it is. Similarly, if A gets scheduled in period 2, this is the cost, this is the benefit, and so on. All right? What you want to do is to maximize the overall benefit, okay, minus the cost. That's the overall optimization problem. So how do we set it up? So we're going to think about what the control variable is going to be, and the control variable over here we'll have as xi, the integers, and we'll define this. Xij means that ith person, in this case A equals 0 and B equals 1, uses the machine in period j. So to be more precise, let's just say x. For example, if x1 0 equals 1 implies, I guess I'm using 1 and 2. So x1 1 equals 1 means that B, what am I calling it? 0. I should be consistent. I guess I'm not. Okay. So 1, 1 means that B gets to use the machine in time period 1. All right? If x11 equals 1, if x11 equals 0, B does not get to use the machine in period 1. Right? That's all it is. So x1, these are what I call indicator variables. The xij's are, I should probably call this over here. These are indicator variables. And this is the most common form of integer linear programming that you'll find. We use indicator variables, and this is why I've got confused with saying 0 and 1. Indicator variables are 0 or 1. Okay, if it's 0, something is not happening. If it's 1, something is happening. And so, we quite often show up, get ILPs with 0s and 1s in them. At any rate, x11 equals 1 implies person 1 uses machine in time period 1. Okay. So, oops, I was trying to turn stuff on. Okay. All right. So that's the meaning of that. So now the question is, what is the objective function? So we can write down the objective function as the following. So what is the overall benefit minus overall cost? So if person 0, A gets the first time period, that's x01, then if that's true, that's 1, then the cost is 10 and the benefit, benefit is, I can't see from here properly. Okay, so let's just put it like this. It's a cost, it's a benefit. So it's 15 minus 10 plus x 0, 2, okay, 6 minus 1 plus x 1, 1, 200 minus 20 plus x 1, 2, 8 minus 5. So this is, the objective function, right? So it's just these indicator variables. So if I do the, this is, clearly that's what it is because this is the assignment. Now, I have to now put some constraints in because otherwise, everything will get assigned to everybody. You can't do that. So what do we do? The two constraints that we have. So constraint 1. Constraint number 1 is that they only have 2 jobs, right? Okay, you can only schedule 2 jobs. They may have actually many more jobs. I didn't show you how many jobs they have. I never told you how many jobs they have. They may actually have hundreds and hundreds of jobs. The constraint is only 2 time periods. So they can only have 2 jobs being scheduled. So we can just say that x01 plus x11 less than equal to 2. That means, 0, 2. So if you get, a person can get assigned to time period 1 and time period 2, that's all they can get. They can't get more than that. You can't actually get any more time periods. So essentially this is a constraint that says can't have more than 2 jobs. And the other constraint is that at any given point in time, you can only have 1 job schedule, which is that x01 plus x11 less than equal to 1. And there's another constraint similarly, x11 plus x12 less than equal to 2, x01 plus x11, x02 plus x12 less than equal to 1. So this is the second constraint. So the first one says you can't have more than 2 jobs because only 2 time periods. And second one says in every time period you can only have 1 job. All right. So that's what I said over here. 1 job per time period. That's this one over here. And this one just says only have 2 time periods. Okay. And that's what's explained over here. So I can now essentially crank up my integer linear programming solver and say here's my objective function. Clearly it's linear in these 4 variables. And I have 2 constraints. I have 4 constraints expressed in terms of linear constraints. And then I'm going to basically say, okay, give me the values of the xi's. and when it pops out, it's going to give me some assignment of xi's, and they will be consistent because of the constraint, and that tells me what to do, and that is going to actually maximize my objective function. Okay? So, any questions on this so far? Yes, sir.
Can the first constraint be combined into one inequality?
These two constraints?
Yes.
How will you combine these two into one? Yeah, you could do it that way. Yeah, saying the total number of jobs in the system is less than or equal to 2. Yes, you could do it that way as well. Yeah, that's correct. Yeah. Yeah.
How does that integer linear programming solver that works? I guess this is a hard problem.
I'm coming to that. So the question is, how does the solver actually do its job? What's hard about it? I'm coming to that. Yes. I just want to give you a sense of how to set up integer linear program. I'm actually going to take it one more step further just to make sure you understand it. But before I do that, I just want to make sure people understand the setup over here. Okay, so what I'm going to do is, I told you earlier that we can have these slack variables, so I'm going to actually show you how to do that just for completeness. And what a slack or a surplus variable does is it converts the inequalities into equalities. So let's just take this one over here, for example. So x01, so we had this inequality x01 plus x11 less than or equal to 1. What we really say is x01 plus x11 plus s1 equals 1. All right, so s again becomes an integer, it can be 0 or 1. So basically, we are adding this extra variable over here, this gives us essentially equalities, inequalities. Similarly, we can add some more slack variables, and if you look at the lecture notes, what you'll find is that you have these equations and written out with slack variables in the form of matrices, and you can actually look at the matrix, what the matrix exactly looks like. I'm going to skip that because it's pretty trivial. There's nothing much more there, nothing much there. Any questions about this so far? Okay, so now let's get into the question of what makes it hard. So what makes it hard over here is actually these kinds of constraints over here. All right. So what's going on is that if I assign x11 as 1, then immediately that means that x01 has to be 0. Right? So I have some assignments of the xi's. I have let's say I have a vector of different x's over here. What happens is each of these constraints actually causes linkages like this. I drew these arrows earlier. Now I'm explaining what the arrows actually mean. That means that if this is 1, then that's got to be 0. If that's 0, then something else has got to be 1. If something else is 1, something else has got to be 0. So all of these set up these cascading chains. So if I change one thing over here, it has non-local effects. Everything else down the path also changes. And that's what makes it really messy. Okay. So we can't just say, okay, I'm going to change this, and it doesn't change anything else. In a linear program, not an integer linear program, but a regular linear program, if I have some function of the xi's, if I change 1 by epsilon, it doesn't make any difference. The overall function goes up by some value. It doesn't change anything. So if you remember, I had the constraint plane or the isoquant plane. I was able to just pull it through by 4 epsilon each time I change one of the variables by epsilon. Here, I can't change by epsilon. I have to change by an integer. If it's a 0, it goes to 1. It jumps up, and immediately all the other constraints kick in, and everything becomes completely crazy. Okay? So that's why ILP is hard, because I can't change something by a small amount and have it to have a small effect. Another way of putting it is that there are no such things as small changes. In a linear program, I can make a small cost and have a small effect. In an integer linear program, small cost can have huge effect. Okay, and this is exactly scheduling. So this particular constraint is scheduling constraint. What are we saying over here? Only one person can be served at a time, because that's what the room accommodates, or the job accommodates. So the machine accommodates only one job at a time. So by kicking somebody else out, they have to be put somewhere else. If they're going to be put somewhere else, somebody else gets kicked out. Again, we have this non-local type of effects. So when you see a problem where you have these kinds of cascading effects, then you know you have something like an integer linear program on your hands. Okay, and so another classic example of this is Sudoku. If you played Sudoku, or how many people have tried Sudoku? Right. So some of you tried it. That's a classic integer linear program, right? Because what do we have? The indicator variable xij basically says that you can define some number of sets, and you can just say the jth element is in, or maybe ijk, the ijth element is in the kth set, right? And when you put it in there, if you take it out, then everybody else changes. And actually, as a homework assignment, you should probably consider writing the interlinear program for Sudoku. It's actually a fun thing to do. And maybe you'll enjoy actually implementing it and trying it out. You can have an LP solver do your work for you in doing Sudoku. But that's a classic example, because you have the setup, and you change one thing over here, you put it in, you fill one value over here, and then everything else over here has a non-Becquerel effect, and that change over here causes effect over here, that causes effect over here. Everything is mixed up with everything else. And you'll find that almost all logic puzzles are actually ILPs. Okay? If you start looking at them, you'll see ILPs everywhere. All logic puzzles essentially are ILPs, one sort or the other. That's why they're all NP hard. So if you open up any puzzle book, you'll say, oh, that's an ILP, that's an ILP, that's an ILP. It's all over the place, it's ILPs. And so this was kind of a fun thing to do, and anyway, it's something that's worth trying out, I guess. How do we solve an interlinear program? So let me tell you about 3 ways of solving it when you have this kind of mess. Okay, so people understand what the mess is. Non-local causality is what's going on, or everything is mixed up in one big can of worms. So when you see an ILP, you kind of have 3 choices. One choice is brute force. Okay, brute force means give it to a solver, go get a cup of coffee, come back, hopefully it's done. If it's not done, go home, come back the next day, maybe it's done. If it isn't done, go home, come back a year later, maybe it's done. Okay, or maybe it's not done. Maybe it's going to take 100 years or 1,000,000 years. You really don't know. Okay, because these are all NP hard problems, and it just doesn't work. So you start with small problem size, and you kind of see how it goes up, and you say, okay, this solver will finish before my thesis is due, so it's okay, it's small enough. All right. If the expected completion time is greater than your thesis completion time, you're in trouble. Okay, then you have to look at something else. So the second way of doing things is basically use heuristics. Heuristic says, look, this problem is complicated. I can't actually find it. So what I'm going to do is I'm just going to wave my hands and say it's optimal, though actually it isn't. And we can be a little bit cleverer than just waving our hands. And the next lecture, I'll talk about what are called heuristic approaches to optimization. We'll consider several approaches, and I'll go through some of these and some techniques. But heuristics are almost always what you resort to. However, there is a nice trick, and that trick is called total unimodularity. Modularity. So before you give up on an ILP, you should always check for total unimodularity, because if you have this, you're lucky. What this means is this. It means that you take the ILP and you give it to an LP solver, not an ILP, so you give it to an LP solver, and it will do its thing, it will come back, and guess what? The solutions will be integers. So even though it's an ILP, and you didn't say make the constraints integers, the solution actually will be in integers. And so this is a kind of allows you to, this basically means it's fast. So it's always worth checking. And for this reason, so let me first explain what total unimodularity means, and then I'll explain how to compute it. So first of all, a matrix. So what matrix are we talking about over here? I should probably start with that. So we're talking about AX equals B, where A and all of these are matrices. X is a vector, B is a vector, A is a matrix. So A is essentially the constraint matrix. So we're talking about this matrix over here. And what are we saying? This matrix is A is unimodular if its square and its determinant is plus or minus 1. Okay? So if you have a square matrix, then and its determinant is plus or minus 1, then it's called unimodular. That's just the definition. Now, of course, A is not square, because if A was square, it would be constrained. There would be only one solution. So matrix A is totally unimodular. It's often abbreviated TUM if every square submatrix has a determinant plus or minus 1. Okay, so we take the matrix A and we find every square submatrix or every rank, of smaller, bigger, whatever, until the largest possible size. And if you look at all possible square submatrices and all the square submatrices have determinants plus or minus 1, then it's totally unimodular. And then we can just take this, give it to a solver, and you're done. Now, in practice, what you do is actually you use 3 rules for total unimodularity. And here are the rules. It's much easier to use these rules. The first rule is all entries are either 0 or plus 1 or minus 1. So if any entry is not 0, plus 1, or minus 1, you're out of luck. Okay. The second thing is that there's either 0, 1, or 2 non-zero entries in each column. And 3, okay, the rows form 2 sets, and just call them A and B, and they follow this. So this is a sub rule here. If a column has two entries with the same sign, one is in A, other in B, and if a column has two entries with different signs, that means plus or minus 1, both in A or B. So the reason I'm giving you these rules are because this is a cookbook, okay? There's some recipe over here. It says, just check these 3 things. The first one is easy to check. The second one is pretty easy to check. Third one, you have to work hard. You have to form these different kinds of rows, A and B. But suppose you can't find it, then life is great. So it's worth the effort to try and find this over here before actually giving up. And just to kind of give you the an example, I have an example over here, and we can check whether it's totally unimodular, whether it is totally unimodular because I made it that way. 1, 1, 0, 0, 1, 0, minus 1, minus 1, 0, 0, 1, 0, 0, and so as you can see, first of all entries are 0, 1, and minus 1, so that's okay. Then we can have either 0 or 1 or 2 non-zero entries. So this has 2 entries, this has 2, this has 2, this has 2, and this has 1, so that's okay. And then the third thing is we have to partition them so the sign thing works. And let's define this as A and this as B. What you find is that if a column has 2 entries that are the same sign, these 2 are the same sign, they're in different sets. These 2 have opposite signs, they're in the same set. These 2 have same sign, they're in opposite sets. These 2 have opposite signs, they're in the same set. This only has 1, so you can put it in either one, right? It's in this set over here. And because of this, we claim that we can partition the matrix into 2 parts. So the integer linear program which has this as A can be given to an LP solver, and it will solve it, and the solution for the xi's will actually be integers, all right, with these constraints. Okay, we haven't actually so these are the constraints on the. We don't actually need to know what B is. It's just constraints on the A's, and if you have these coefficients on the constraints, you will actually get integer solutions. And so this becomes quite a powerful way of getting things going. All right. So let me pause here. Any questions about this so far? Yes.
What do you mean that every submatrix has determinant plus minus 1?
It means that every submatrix of this, every square submatrix of this has a determinant plus. So if we take this as a submatrix, that's a submatrix, that's a submatrix, that's a submatrix, etc. right? So I can, and then have other submatrices 2 by 2. I can look at 1 by 1, 2 by 2, 3 by 3, and 4 by 4 submatrices of this 5 by 4 matrix, and then all of them have a determinant of plus or minus 1. Okay, and then that's a theorem which I haven't proved. Obviously, you would say that if these conditions hold, then every square submatrix of every order has a determinant of plus or minus 1. Yes?
But is it not necessary?
What is not necessary?
So you just said that it's sufficient.
So-
These rules are sufficient. Are they also necessary?
Good question. I don't know. I know these are sufficient. I have to look up and see. This is these rules are from Papadimitriou and Stiglitz in chapter 13. You can look it up. But I don't remember whether it's necessary and sufficient or just sufficient. Yeah, I'll have to look it up. Yeah, I don't know. But certainly they're sufficient. Yeah. Yes.
Mohammed Ali,
Yes.
can you please explain how you divide this matrix into?
How did I divide this?
Yes, sir, I missed it.
Oh, by inspection. I made the matrix up, so I also chose these to be nice and clean. But you need to be able to find at least one partition into A and B such that you can have these rules. These two, if they have the same sign, they're in different sets, and they have different sign, they must be in the same set. That's what you want.
But we will consider each column or?
No, we have to partition all the rows.
Okay.
So first we try some partitioning, and then we see if we can achieve it. If not, we try different partitioning. So already here we're doing kind of extra work, but maybe it's not too bad. I mean, this is, as I said, by inspection. There is no algorithm that says try it this way. This is essentially Sudoku all over again. Okay, say, okay, I'll put this row in set A. Oops, that's not going to work. Okay, let me put in set B. It's actually not that bad, because you look at this row and this row, let's say, they have to be in different sets. So we got that already done, right? They have to be in different sets. And we look at these two rows, that these two have to be in different sets. So already we have, this is only possible partitioning. And if we had got something like this, that would not be totally unimodular, because these two are the same sign in the same set. So it's not too hard.
Consider only 1. 0 will not consider.
0 we will not consider, that's right. So because we look at this, if in the column has 2 entries with the same sign, 0 doesn't have a sign. Yeah, it's just the ones. Yeah.
Probably I will understand.
Yeah. You can take, yeah, yes, in the back.
Sorry, can you partition the matrix vertically instead of horizontally?
No, you partition the rows, not the columns. Yeah, that's the rule. Okay, it's a cookbook. I mean, you can't. It says put salt and you put sugar, it doesn't taste good. Okay, you put salt in your coffee, it doesn't taste good. Same thing. It's not modular. Yes.
Does A and B need to contain the same number of rows?
No, it doesn't need to contain the same number of rows,
So
but
at least one row, right?
at least one row. That's right. Yeah. Yes.
When considering submatrices of this matrix,
Yes.
should we consider only adjacent columns and adjacent rows?
That's right. That's how you define submatrix, right? You submatrix. Oh, wait a minute. Can you? Yeah, they'll be adjacent. Yeah, because you're going to consider. Let me now think about that. You can consider submatrices that are non-contiguous.
Of one row and one column, and the remaining elements.
So the definition says submatrices, but really what you do is follow these rules. Okay, if you follow these rules, so I don't know. I mean, as I said, I'm just an explorer in this continent, right? I've been given this recipe, and now I have to go back and see whether you can, in fact, drop it or not in the definition of the submatrix, but I'm not really sure. Yes?
I think it shouldn't change anything, because if we change like just names of variables.
Yes. Yeah, it changes the orders. Yeah. So I would think that it should be okay. I mean, that you would actually, any selection should be okay, but I just want to make sure there are no corner cases. You're right.
That's the definition of submatrix.
You can choose any set. Okay. All right. So thank you, Chan. Yes. So you can select anything. We have resolved it because, yeah. Okay. Yeah, you're right. So any relabeling obviously is going to give you different selections. So, and these are just representing inequalities or equalities. So we should be able to choose any submatrix, any set. Yes.
Is the example you're giving unimodular?
This one. Well, not right now. Now it is. I had changed that 0 to a 1. Now it's unimodular, but not.
Take the third square you've drawn.
The third square I've drawn, this one. It's
The next one.
the next one.
This matrix is determinant 0.
Just 0. You're right. So why did my rules work? Okay, let me go back and see what's going on here. Okay, so
Probably because like the condition is if it's for non-singular.
yeah, it should be a yeah, because the determinant of this is going to be, it should be non-singular. Every square non-singular, because that one is going to have the denominator of 0, right? It's going to be a 0 by 0 form, so that's not going to work. Yeah.
So actually, I have a reference here.
Yeah.
So it's the total unit modularity.
Yes.
Actually, is if every square submatrix of A has determinants -1, 0, or 1.
Okay, -1, 0, 1. There's what did I say over here? Hang on. Did I say, hang on for a second. Page, the wrong page here. Oh, I very carefully managed to skip the page in my notes over here altogether. Okay. Let's see over here. Page 15. Where is page 15? Missing. Okay. What does the note say? I don't know actually. Oh, there we go. Because determinants of 0. So you're saying it should be -1, 0, or +1? Yeah, I could have 3 things. Okay. Let me check on this. Okay. I mean, I know that these rules are correct, and I might have made an error in putting that down, but yeah, this is just, basically it's a definition. This is what we have here. Okay, so let me make a note to myself. Check. Okay, I know that these rules are correct, and but I could be wrong on this definition over here. Okay, I'll double check that. Okay, this is a great time for a break, for me anyway. I have a few announcements that I wanted to make. So the first thing, and chances are pretty good I made a mistake. I hope not. Okay, let's now use linear programming for something interesting, which is weighted matching. Okay. So, in many cases, we have the following problem. We have some kind of graph, which is what's called a bipartite graph, which means we can divide the vertices into 2 sets, like so, and the edges always go from one set to the other, like this. So, we never have edge like this. That's not allowed. Okay. So that would make it not a bipartite graph. But if edges are like this, so crisscross pattern, okay, then it's a weighted matching. So then it's a bipartite graph. So now what we can do is on each edge we can define some weight. Let's call this node U, U1, U2, U3, U4, U5, and then this, let's call this V1, V2. Then you can define the weight W, in this case U1, V1, and that's the weight of that edge over here. And so on each edge we can have some kind of weight. Now, what does this weight mean? What's going on over here? Let's take an example that we've had earlier. These V's on the right-hand side could be time slots. Okay, maybe you have a machine that has 5 time slots, time slot 1, time slot 2, time slot 3, 4, and 5. So those could be time slots. And then on the left could be people's jobs. So you can say, well, my job can be scheduled at this time slot, or it could be scheduled on this time slot. If it gets scheduled here, that's the cost minus benefit. If it gets scheduled here, my cost minus benefit, but benefit minus cost is WU1, V2, and so on. So we can think of that as being a particular scheduling problem represented in this form over here. Okay. So in general, we can think of very many other problems which fall into this category, where we have these vertices and we have these, so we have 2 sets of vertices and all edges go from here to here. Obviously, in our case, of scheduling, we're never going to have an edge from one U to another U, because all the requests go to time slots, right? Now we can also think of some funny situation like this, where you could have, let's say, two machines, and you can have edges going to this machine or this machine at this time slot, that time slot. Again, we can club all of these into one set of vertices, so that's fine. That's not a problem. We can make these vertices as general as we wish. Okay. So weighted matching, it turns out, can be solved in many different ways, just like network flow can be solved in many different ways. And the approach I'm going to use over here is to represent it as a integer linear program. Okay. So what is a matching? A matching is a selection or subset of edges which have the property, like this one over here, that no two edges share a vertex in common. Okay, no two edges share a vertex in common. So if this is in the matching, this edge can't be. If this is in the matching, this edge can't be. And this is in the matching, so that edge can't be, and that's in the matching, so those edges can't be, because so we have the same kind of rules that say if this happens, then that can't happen, and that happens, that can't happen, and you see that right away over here. So this is a matching. Okay, a matching is maximal, or in this case, a weighted matching is maximized if the sum of the edge weights over, so M belongs to the matching M and WM. So I'm here M, I'm using, so the edge U1, V1 I'm calling as M just for convenience, and I'm basically saying that for some matching M, so here the matching M is just this one and this one and this one, and I'm summing all the edge weights. Okay, so we just want the objective function to be this. So we want to maximize the sum of the weights. Okay, so that's pretty straightforward. And because of the summation, clearly it's a linear function, and we get that straight out of we get that right away. Okay. Now the next thing we want to do is to make sure that that we don't share vertices in common, and we can express that as two constraints. One is that essentially over all the edges that depart from here, okay, only one belongs to M, and of all the edges that arrive into here, only one belongs to M. Okay, and so if we can express that, and let me just be consistent with what I said. Oh, I guess I expressed it slightly differently. Just okay. So let me use the indicator variable x u v implies edge from u to v is in M. All right, and then what we'll say is that the objective function is just sum the weight of uv times x uv over basically uv belong to M. So it's a different way of representing this, doesn't really make any difference. And then what you're going to say is that for all u, the sum over w, which is a new variable, x uw, which is, so that's what you're operating over, equals 1. And for all v, sum over w, x w v, x w v equals 1, and x u v belongs to 0 1. We can't have fractional matching, so you can't say, well, I'm going to use half of this and half of this over here. Everything has got to be either in the matching or not. So right away, x is of the indicator type that we saw earlier, and what you're saying is that we want to maximize this sum of products. So these are the constants given to us by the graph. These are the control variables, x u v, and the x u v's are chosen to be in the matching or not in the matching, and these are the constraints. They're pretty straightforward. Okay. And if we throw this into an integer linear program solver, it will basically spit out the values of the x u v's such that it's an actual matching because these constraints hold, and in fact it maximizes the objective function. Yes?
I have a question about this objective function.
Right.
Do we sum over all edges here? Or because we don't know what matching we have fixed, right?
Oh, wait a minute. Yeah, we have to, that's right, this belongs, I should have been careful, yeah, over all it's over all UV, for all UV, for all U, for all V, that's right, because XU will be set to 0. Will be set to 0. I need to make a correction over here. I have to put in U for all U for all V. Yes. Okay. It's always dangerous to do math in real time, at least for me. I'm sorry. Yeah, basically we're saying for all combinations of U, V. Now, if there is no edge, then the way it can define it to be 0. Okay, then it doesn't matter, right? So it doesn't really matter how you define it. So essentially an adjacency matrix that you can use over here. Yes.
I think the first constant should be a non-equal.
This one. This one.
Constant, yeah.
Oh, because you're.
It's not a one-to-one matching.
Yeah, I skipped a step. I was going to add I was going to actually make it into a complete graph. But if you don't have, what I should have done, which I did not, was to complete the graph first. Basically, adding all these 0, 8 wedges from everywhere to everywhere. If I do make it a complete graph, then it's equality. If it's not, it's inequality. Okay, so I should have done that. Yeah.
Then if it is complete, maybe the size of two sides are not the same.
The sides of two sides are not the same. Okay. So what I'm saying over here is that I must have at least one edge from U to the other side. You're saying, but if I choose that to be one of these dummy edges, it doesn't really matter, right? It's not adding anything. Because it'll get thrown out because the preferred edge, it's never going to, this maximization is going to basically throw out the dummy edges because you're always going to use a better weight when you have it. So it doesn't really make any difference over here. Yeah. But I should have said complete the graph first. Okay. Sorry. Any other questions about this? Yeah. So let me double check and make sure I didn't screw this up. So, yeah. So if you complete it, then we essentially zero weight edges help us make this into an inequality. Otherwise, it would be inequality. Okay. Any other questions? Okay. So the whole point here is to illustrate that we can use these indicator variables. We have to be a bit careful how we define them and so on, and I was a little bit sloppy over here, but when you're careful and define it properly, you will actually be able to pose it as an ILP, and then hopefully the problem is not too large, you can use it. Again, this is not the preferred way of doing it, it's just illustrative that problems that you would not necessarily think of as being ILP, in fact, can be represented in this fashion. So generally speaking, when you see a problem where things can be in or out of the solution, anything can be in or out of the solution, you can represent that in the form of an ILP. It may not be the most efficient way of doing things, but it certainly is a doable way of doing it. It's a first step forward. Okay. Any questions about that? Yeah.
Is there any approximation algorithm for this ILP? Theoretically, we can approximate this problem.
Can you approximate ILP? ILP forms in the NP category. So for specific types of ILPs, you can probably find approximation algorithms. But to my knowledge, I mean, again, this is not something I'm an expert on. To my knowledge, ILP, when it's shown to be an interlinear program, it is potentially NP hard. Okay. Unless you have this total unimodularity, in which case, yeah.
NP hard, maybe an approximation algorithm can be helpful.
Yes, it could be, but I'm not aware of that. So if you find out, let me know. Okay. Okay, I want to switch gears and actually move on to dynamic programming. The next thing, and this is the part where I want to kind of go a little bit slowly and carefully. And this is quite a powerful technique. So I'm going to start out with sort of the intuition of dynamic programming, and then maybe after a short break, I will continue and give more details and the actual technique. So dynamic programming is a technique where we want to solve a large problem, but we want to do it sort of fast. And what we exploit is that the problem has what's called an optimal substructure. So what that means is that the optimal solution to this problem contains within it the optimal solution to a smaller problem, and that contains a smaller problem, and so on and so forth, until we left with a really tiny problem to which the optimal solution is obtained by inspection, right? So for those of you who are familiar with divide and conquer, right, you kind of know how to do that as well. So divide and conquer says, I have a large problem, I'll express it. So I have some problem P of size n. I'll express it in the form of some function f of p n minus 1. Okay, and then I'll go solve p n minus 1. And then when I have that solution, apply the function, I'll find the value of p n, right? So this is the classic way of doing divide and conquer. Divide and conquer and dynamic programming are related but not the same. In divide and conquer, we can have an explosion. We can have the following problem. I have problem P of n, and it breaks up into, let's say, 3 problems or 4 problems of size n minus 1. And this P n minus 1. And then each of those breaks up into 4 again, and now you see the problem. Essentially, I have something over here that's growing, okay, exponentially. So I have over here, this graph grows faster and faster. So I don't want to actually solve this because I have more and more and more subproblems. I thought of solving one problem, I have to solve 4, and then I have to solve 16, and so on. So I have to essentially solve 4 to the n subproblems, and that's just too much, right? It's exponential in n over here, right? It's like e to the n. So divide and conquer by itself can lead to exponential growth, okay, because everything just blows up on you. But with dynamic programming, what happens is this. We essentially get not a tree, but we get a graph. In fact, a nice graph where it turns out that this subproblem and this problem are the same, for example, and this problem and the other guy are the same. And maybe we find some other relationships. And this means that we don't actually have to solve lots more. We're reducing the solution space, okay? So maybe this guy and this other guy are the same, etc. So once you find these, once you solve this over here, when you come back over here, you just look it up and you say, oh yeah, I already solved that one. I don't need to do it again. And this is what's called memoization. It's like memorization, but it's not. It's called memoization. It just means I create a memo, like, okay, I solved that one already. So in a dynamic program, what you're looking for is this. You're looking for the optimal substructure, okay? That is important because that means you can recurse. But that's the same thing as in divide and conquer. But in addition, we're also looking for the ability to not have to solve the problem over and over again. In fact, the ideal dynamic program looks like this. Once you solve Pn, you break it up into form of Pn minus 1. What we want to do is to form it so that we solve Pn once, Pn minus 1 only once, Pn minus 2 only once, Pn minus 3 only once, and in the end we actually solve each subproblem just once. It's reused many, many times, but we actually solve it only once, which means we get order of n, because you just kind of figure out Pn, Pn minus 1, Pn minus 2, etc., all the way down to 1, and then, hey, you only did that once. So in fact, what looks like a very large problem turns out to be just a sequence of sort of n computations. It just may be that I have to combine these, or maybe I have to combine these two, and these other 3 guys in some way, and so on. But that's okay, because what we can do in dynamic programming is that we can use what's called a bottom-up or top-down approach. Okay, so bottom-up approach says, let's find the simplest subproblem, we'll solve that, and then we'll solve the next one, we'll solve the next one, we'll solve all of these guys, okay? And then what we'll do is we'll just start combining them to create these solutions that we need, and as we combine these solutions, we'll find the final solutions. That's the bottom-up approach. And it sounds a bit hand-wavy right now, but I'll talk about how to do the shortest path problem in graphs, and that you'll see how that shows up right away. And the top-down approach says, okay, I'm going to break it up into these 2 subproblems, and then I'm going to recurse, in some fashion, and then similar, so again you have that's this approach over here. So I have this is the size 1 problem, and this one is the n minus 1 problem. So in the top-down approach, we break up the Pn problem into a smaller subproblem of size 1. We examine the inspection and a larger subproblem, and you recurse all the way down. In the bottom-up approach, we figure out 1, and then we use that to construct 2 to construct 3, kind of work your way up. So it's essentially something like induction And that's the way we do it. So, let me take a break in a minute. So I want to kind of tell you what to look for when you can apply dynamic programming. Two things. Look for the ability to recurse, to express the problem in terms of a smaller version of it. So if you have a problem of size n, I can express it in terms of problem of size. I should probably not just say n minus 1, but n minus 1, n minus 2, etc., all the way down to p1. Just smaller. It doesn't have to be, just n minus 1, okay? But it's just smaller, because then I can use this, I can use something over there, combine it to get this. And the second thing is that we want the ability to reuse the solutions. We don't have to solve new problems all the time, okay? So typically the way dynamic programming is taught, it turns out to be hard to see both of these at the same time. So first I'm going to show you a problem that is not an optimization problem at all. Actually, it's Ackermann's function. And I'll show you how to compute Ackermann's function, because the Ackermann function computation looks just like dynamic programming, even though it isn't actually an optimization problem. And then we'll consider how to do what's called the Floyd-Warshall approach to shortest paths using dynamic programming. Okay, so let me take a break. But before I do that, are there any questions about this over here? Actually, how many of you have seen dynamic programming before already? Okay, pretty much the whole class has seen it. Okay. Good. So this is just going to be a refresher. Okay. So let's stop now, and I'm going to just talk about what I've been doing it for 22 years. So it's the least I can do. When I was teaching about 10 years ago, I promised the class that in the last class I'll do flaming torches. But the security people wouldn't let me do it. They said it was a fire hazard. So, also, parents of some of the students are not too happy, especially those sitting in the first row. So I did knives instead. Okay, let's do something more interesting, which is Ackermann's function. So, or it's not Ackermann, we're doing Fibonacci. Oh well, Ackermann's is similar as well. All right, so what's the Fibonacci sequence? Why did I think it was Ackermann's anyway? FIB, okay, it's 1B, BONACCI, Fibonacci sequence. So how many people have heard of the Fibonacci sequence? Okay, it's kind of, all right. How many people know what Fibonacci's real name was? I bet you didn't know Fibonacci was not his real name. Fibonacci was just the contraction of Phyllis Bonacci. What does that mean? Son of Bonacci. His real name was Leonardo. Okay, so Leonardo, son of Bonacci. So he called himself, I think, Leonardo Fibonacci as an actor and as a short form of Phyllis Bonacci, and he got named as Fibonacci. So that wasn't his real name, but very, very few people know that. Now you do. All right, so the sequence looks like this: 1, 1, 2, 3, 5, 8, 13, etc. And we know that the ratio goes to a golden mean and shows up in many other different places. We're not trying to do that. All we want to do is like this. Basically saying F1 equals F2 equals 1. And for n greater than 2, Fn equals Fn minus 1 plus Fn minus 2. All right? So that's pretty straightforward. Now what I want to do is to show the notion of optimal substructure and composition and the need to limit subproblems in this particular thing. So what we have over here is this. This is what I've been calling Pn, right? I have a problem to compute of size n, and what I've shown over here is almost the simplest form of decomposition. It allows, you need to solve two subproblems, Pn minus 1 and Pn minus 2. Okay? So let's just show something. Let's just say I want to compute F100, and this means I need to compute F99 and F98, and this really immediately shows that I have optimal substructure, right? I've just written it that way. Now the nice thing over here, we're going to look at memoization, is that F99 in turn is F98 and F97. But guess what? This F98 is same as that. All right? The same as that. So what I'll do is, and similarly 98 is F97 and F96. So what I can do is like this. I can solve, okay, either top-down or bottom-up. So in the top-down approach, I'll say F100 is F98, F98. Okay, let me just set aside 99, or let me set it 98 for now. I'm going to solve 98 and 97. Okay, and then for 98, I'm going to set aside the right-hand side. I'll set 98 is 97, 96, etc., all the way down. And as I come back up, what happens is all these things that I need are already computed for me, okay, in the past. So what I need to do is just keep an array like this, which looks like this. I have over here F1, F2, all the way up to F99. So when I compute, let's say, F98 over here on my depth-first search, I'm going to enter F98 over here. This is F98. All right? And when I need it, when I come back on the depth-first search, I'm going to come back all the way to the top and then go down this subtree. When I go down this subtree, actually, everything I need over here has already been done because I pretty much explored the entire space and kept it in this over here. How many entries do I need? I just need 99 entries. Okay? And after I have 99 computations, I can spit out F100 and I'm done. Okay? So that's the beauty of dynamic programming, is optimal substructure and memoization, which means that I am reusing these entries, okay, in the substructure. So whenever you see this, you're in great shape. You're going to say dynamic programming. Here I go. You've set up the appropriate memoization structure, which is essentially indexed by the problem size, and you're off and running. You're done. Okay, you can just throw it into again, just like ILP solvers, your dynamic program solvers, where you just express the problem, it'll do it for you. Or you can write it, it's a few lines of code to express this. Okay? Any questions about this so far? All right, so obviously we're not optimizing anything over here. We're just kind of computing the Fibonacci sequence. We can compute Ackermann's similarly, because Ackermann's is, I'm not sure it has optimal substructure anyway, but Fibonacci certainly does. And essentially any recurrence relationship that you want that has these kinds of cross ties can be represented as a dynamic program and computed quite easily, any kind of recurrence relationships. Okay, so let's do something a bit more interesting. Okay, so this is a very, very simple thing. Let's try and compute something more exciting, which is I want to find the shortest path in a graph. So I have some graph over here. Graph consists of some vertices and some edges between these vertices. And, you know, let's say I have some vertices over here. And I have some weights on these edges in the usual way. And let's say this is 1, this is 2, then W12 is the weight on this edge. If you don't have any weights, we'll just set all the weights to 1, in which case, you know, I can just have equal weights to everything. What I want to do is to compute the shortest path from some node I to some node j, okay, in this network. Okay, that's what I want to do. And I'm going to show you how to do this using dynamic programming. Okay, now again, for shortest paths, you know, we know Dijkstra's algorithm, you know, there are many other approaches, but let's just see how to do it using this approach. It's called the Floyd-Warshall algorithm. Okay, and the first thing you need to do, Floyd-Warshall, is to number all the elements, all the vertices with integers. So you guys, you know, call this 1, call this 2, 3, 4, 5, 6, 7. It doesn't really matter how you number them, but it's important that you number them. Okay? Now, we need to find, we're going to pick some I and some j. I'll just shade them over here. And I want to find the shortest path from I to j. So what is the problem structure? How do we find the optimal subproblem? Now, this is a bit tricky, and so I chose this because I'm illustrating that it's tricky. I'm going to define something called S, I, J, K, and this is a path from I to j. Okay, that's easy. But what is this k for? We say that uses intermediate nodes or intermediate vertices whose index lie in 1 to k. In other words, we can't use k plus 1. Okay, and such a path may not exist. Okay, it may not exist, that's fine, but if it exists, this is the shortest path. And strictly speaking, we should be using this S, I, J, K, the modulus as the length, but just because we know that the length can be trivially computed, I'm not going to put the modulus. I'll just Sijk also represents the length of this path. We'll just sort of abuse the notation over here just for clarity. Okay? All right, so I'm given some I and I'm given some j. Now the shortest path obviously is going to be S, I, J, N, where N is the number of nodes, right? Because obviously the shortest path is going to use some indices or some vertices, and I don't know whatever they are, but they all got to be smaller than N because they're only N, the number of nodes equals N, right? So clearly it has to be the case that Sijn is what we're looking for. How do we express this as a subproblem? So we're going to express it like this using the following observation. So what we're going to do is we're going to compute Sij k in terms of Sij k minus 1, okay? And let me be careful about how I do it because it's easy to yeah. So I'm going to maybe I should not put ijk over here. I'll put dot comma k minus 1. The important thing is k minus 1. All right. So I'm going to essentially pick up solutions which have k minus 1 as the parameter of interest, and these two are unbound. Okay. So if I have all solutions of k minus 1, then I can get the kth one. Okay. That's the recursion that's going to happen. All right. And then what we'll do is we'll use the same trick to go from k minus 1 to k minus 2, k minus 2, k minus 3, all the way down until we get to 1. Right? Then we'll do xij1. That means can I go from I to j using an intermediate node whose vertex number is 1. Either I can or I can't. If I can go, what's the path length? And if I can't, well, it's got infinite path length. I don't have any path possible. Okay? So we express this in the form of a recursion which says something like this. So okay, let's see what's the observation. The observation is that if I'm going from I to j using these nodes, either I'm going to use either I'm going to use the kth node or I'm not in this path over here, right? Either I use kth node or not. Okay? That's got to be true. Okay? If I am using the kth node, what does Sijk look like? Okay? So we can write down this recursion and explain it after. Let me just write it down before I. Okay, Sijk equals min of. Okay, so let's look at this recurrence over here. So let's say that the path from I to j did not use the node numbered k, right? Didn't use it. K was not necessary. That means it must be the case that I could have got from I to the j in the shortest path just using k minus 1. I don't need the k1, right? In that case, Sijk is nothing more than Sij k minus 1. Because I didn't use the kth node. But if I did use the kth node, I have to go through the kth node. How do I go through kth node? Well, obviously, I'm not going to use the kth node itself in the path to go from I to k. So it will be sik k minus 1, and then from the kth node, I have to get to j. Again, I'm not going to use the kth node again, right? And what's the sum of this path length? Well, it's the sum of this path length plus this. I take these two, add it up, and I compare that with this, and I take the smaller, and I set that to sijk. Okay? So just to give an example of this, okay, so here is my I, here is my j, and here is my k. So we're just saying the path looks like this, or the path looks like that. Either I go through the kth node, or I don't. So if it doesn't go through, then sijk is the same as sijk minus 1, whatever that is. And if it goes through, it must be the sum of these two paths, sik k minus 1, skj k minus 1. And I write this over here, and that gives me recurrence in terms of what? Something, something k minus 1. Okay? So now what I can do is I can compute this table, which for every ij value, it computes basically sij1, and then, for all ij, well, that's how many terms? That's n square. That's n square entries I compute. Then I compute sij2, okay, for all values of I and j, using this values over here and this recurrence over here. All right? And simply by doing this, okay, for n times, I can find the value. So it's an order of n cube algorithm, okay, and that gives me the shortest path from I to j using dynamic programming. Okay, it's not going to be exponential, it's polynomial, it's n cube. Okay, any questions about this so far? So, a couple of observations over here. Using dynamic programming makes things easier. Well, first thing, it isn't making it easier. If you look at Dijkstra, Dijkstra actually is an easier thing to understand than this. I can explain Dijkstra much more easily. So it's kind of tricky to do it properly. You have to do this indexing. You have to have this tricky definition that intermediate vertices have an index that lies in this. So what was the motivation for this tricky definition? The motivation for this tricky definition was for us to be able to recurse down. So you have to think very hard about how do I express it in smaller terms, and sometimes it's not obvious. Sometimes you have to think about clever ways of bringing down the problem size, and this is how you do it, because normally when you think of paths, you don't think about intermediate nodes. So you kind of have to think about it, reduce it down one level, and then you have to figure out the recurrence over here. And once you do recurrence over here, then you'll find that actually it turns out pretty well, and then you have to figure out the memoization. The memoization is this, sij1, then that gives you all of these, and you do sij2, and when you compute sijn, actually you get a bonus, which is you get all pairs shortest paths for free, okay? Because you're doing it for all ij. If you do a memoization this way, you get all pairs for free in order n cube time, which is not so bad. And in fact, a variant of Floyd-Warshall is what is used by Ospf, because in Ospf, what do? We use Ospf, for those of you not in computer networking, is the open shortest path first protocol, which essentially distributes what I call link advertisements. It's saying, I am a node here, these are my neighbors, that's a neighbor, that's a neighbor, that's a neighbor, that's a neighbor. Each of those is called a link state packet. It's flooded everywhere in the network. So everybody in the network gets this graph right here. And once they get this graph, what they do is they run Floyd-Warshall, and they get the shortest path, and they say, aha, if I'm 5 and I want to send something to 3, I'd better send it to 4. And they put that in the IP routing table, and then it goes to destination along that path. So this actual algorithm, it's invented in 52 or something like that. In fact, there's very practical applications. So Ospf is widely used. In fact, Waterloo runs it. In fact, computer science department switched over to Ospf 2 weeks ago. So 2 weekends ago, there was no network connectivity in the department because after many years of rigor mortis, we switched from static hand-configured routes to Ospf. So this is, in fact, something that's happening right now. Is a question somewhere? Yes?
Question about Ospf. So does each node take n cube time, or do they do some sort of sharing?
No, they do. Each node individually computes the shortest path. So Ospf doesn't scale very large. So Ospf is what's called intra-domain routing protocol. We have roughly 100 to 200 nodes. We don't have more than that. So. Any other questions about? Yes.
Is it guaranteed that none of those two passes has any vertex in common?
Yeah, it has to be the case. These two things, right? Because this uses only vertices up to
No, I mean
these two.
these two passes may have some vertices in common.
Oh, they may have some vertices in common?
Yeah.
If they do, then we're going to have some funny situation, because let's just say this is k over here and it has some path like this to get to k, right? This is I and then this is j, right? You're saying that the path, the shortest path from here to here includes this. Well, if it does include this, I can always eliminate that subpath and have something shorter. So that will only happen if some edges have negative weights. And in this algorithm, we are not allowing negative weights. Now, there are variants of the algorithm which allow negative weights, but then you can get into very funny infinite looping situations.
It happens, but we ignore it.
Well, it will go away. It will be taken out, because the shortest path from I to j cannot repeat the same vertex twice, because then that means it has a loop in it. Right? The shortest path cannot have a loop in it, because I can always eliminate the loop and make it shorter.
We didn't define S as shortest path.
I did. I sure did. Oh no, S is the shortest path. That's why S, sorry, I forgot. Shortest. The shortest comes in because of the min. That's why it's the shortest. Yeah, I'm sorry. That's why S stands for shortest. Yeah. I think I said it, but I didn't write it, but it is the shortest path. It is meant to be the shortest path. Any other questions about this? So in the homework assignment, I've asked you to use dynamic programming to compute a string matching problem, or actually, yeah, and that actually shows up in DNA analysis when people have databases of strings, which is just DNA, and you're trying to find substrings, but you want to do a non-exact matching. Okay, I'm going to pause here and just going to give you a brief preview of what happens next. So we're done with these two things, dynamic programming, ILP, both very powerful techniques. And I'm going to switch into nonlinear programs. So in all these situations over here, we have kind of a nice optimality criterion. In nonlinear program, we get this situation where the objective function is not a linear combination of the inputs. So I have, let's say, e to the x1 plus, something else, plus x2, something like that. This is, if I change x1 slightly, my output goes up a lot, right? So it's not linear anymore. And it may not be nice like an exponential. It could be anything arbitrary. So when you have these kinds of situations, in fact, in some cases, we don't even know what the function is. We kind of have to optimize using heuristics. So we'll first focus on situations where the system is non-linear, but the function is known, okay? Where I'm trying to optimize some function O, and this function is known as a mathematical function. In fact, it's known to be twice differentiable, which means we can start doing some nice things with it. But then we'll get into even more horrible situations where we don't even know the function. Right? We don't even know the function. And then how do you optimize that? So we'll kind of look at some of those techniques over there. Okay, I think that's all I have for now. And yeah, we'll meet on Tuesday. So this, yeah.